Okay, so using Cramer's rule, treating u1 prime and u2 prime as our missing variables. We can do 2 by 2 determinants to solve for u1 prime and u2 prime. Okay? The denominator for both are just the coefficients of the variables that we're trying to solve for. So in this case it would be y1, y2, y1 prime, y2 prime. And then same with the other one, y1, y2, y1 prime, y2 prime. And then the numerator, if I'm looking for u1, in the u1 column, I'm going to get rid of y1 and y1 prime, and instead I'm going to put 0 and f of x. And I'll leave the coefficients of u2 prime as y2 and y2 prime. And similarly with y2 prime, get rid of the y2, y2 prime coefficients, replace those with 0 and f of x. And then the x, or the u1 prime coefficients, y1 and y1 prime, are good to go. Okay? So, here's what we're going to do. This denominator we are going to call w. This numerator we're going to call w1. This numerator we're going to call w2. And at this point we can calculate this. We can go back and figure out what u1 and y1 are, what u1 and u2 are going to be, so then we can plug it back in to get our general solution. So let's recap all the steps that we're going to take. Okay, so here's our summary, and then we're going to actually go ahead and do a few problems with this. Okay, so number 1, given an equation that is in the form of y double prime plus py prime plus qy equal to f of x, first, we find the complementary solution. Which is done by making this homogeneous, using the auxiliary equation or differential operators, whatever you prefer, to find y1 and y2. Once you know what y1 and y2 are, we're going to go straight to finding w. And let's just rewrite what w is. What's w again? Yeah, it's easy to remember. Take the solution, take its derivative. Take the other solution, take its derivative. That's how you fill it in the columns. Okay? 3. Find w1, which is replacing this column with what? Instead of y1, y1 prime, we use 0 and f of x. Other column stays the same. We go ahead and find w2. And we just float that 0 and f of x now to the second column, and we leave the first column as is. Okay? 4. We're going to find u1 and u2 by integration, which should make sense because these formulas up here told us what u1 prime and what u2 prime are. So naturally, we're going to integrate u1 equals w1 over w, u1 prime, and u2 prime equal to w2 over w. And then lastly, oh, hold on. Let's add this into part 4. So once we have u1 and u2, we can put together the particular solution, which will be u1 y1 plus u2 y2, since that's how we defined the particular solution. That's how we will put it back together. And then our last step is to go ahead and put the general solution together, which is complementary plus particular. Okay, so that's kind of the outline. It seems like a lot of work, but it's actually not too bad once you get this thing going. Okay, let's do an example. Let's say you wanted to solve y double prime minus 4y prime plus 4y equal to x plus 1 e to the 2x. Just to illustrate a point here, do we have to do the method that we introduced to solve this equation? What else could we do? We could use annihilation, because we know how to annihilate e to the 2x. We would use d minus 2. Since we have a linear term in front of it, we'd make it squared, right? So we can do it that way. But just so we get the idea of how this works, we're going to go ahead and use this variation of parameters method. Okay, so first we're going to go ahead and find the complementary solution. So looking at the differential equations left-hand side, auxiliary equation is m squared minus 4m plus 4. We set that equal to 0. We factor. We get m minus 2 squared. So we get a repeated root, bless you, a repeated root of 2. So what does our complementary solution look like? Yes, plus. Good. So here's our complementary solution, and here is y1, and here is y2. All right, so we're going to go ahead and find w, which is essentially just the Wronskian. We take y1, which is e to the 2x, take its derivative, which is 2e to the 2x. That's our first column. We take y2, which is x e to the 2x. And in hindsight, I probably should have expanded my vertical bars here. Product rule gives us 2x e to the 2x plus e to the 2x. Let me zoom in real quick so it's clear. So e to the 2x, 2e to the 2x, and then x e to the 2x, and then 2x e to the 2x plus e to the 2x. Sorry about that. It's kind of small. Okay. So let's figure out the determinant. Multiply that out. We take this term times this bottom right term. So that gives us 2x e to the 4x plus e to the 4x. And now we subtract these two terms product, which is 2x e to the 4x. So w is simply e to the 4x. That is our Wronskian, which we're also calling w in this method. So now we find w1. w1 we simply do what in this first column? 0. And what's f of x? Good. So x plus 1 e to the 2x. And now we leave the second column as it is, x e to the 2x, 2x e to the 2x plus e to the 2x. Multiply that through. First term is 0, and then we subtract the product of x, x plus 1, and e to the 4x. So I'll just leave it like that for now. W2 same idea. First column stays. Second column gets replaced with 0 and f of x. So now we get x plus 1 e to the 4x minus nothing. So there's W2. And now let's go ahead and find U1. So U1 prime is equal to W1 divided by W, right? Can you guys see what's going to happen? If I take W1 and divide it by W, what drops out? E to the 4x. So this is just minus x squared minus x. If you go ahead and multiply negative x with x plus 1. So then U1, if I integrate, U1 is going to be minus 1/3 x cubed minus 1/2 x squared. Okay, we are not going to use any constants here. Since we already have more other constants in the equation, we have no need for them here. All we care about is this main function. And then we can repeat U2 prime is W2 over W. What's that going to be? Oh, I'm too zoomed in here. Hold on. Okay, so what's U2 prime going to be? X plus 1. E to the 4x drops out again. We take W2 divided by W. E to the 4x cancels out. You get x plus 1. You integrate. So U2 is going to be what? Good. So particular solution. Remember, the format is always U1, Y1 plus U2, Y2. So U1 is minus 1/3 x cubed minus 1/2 x squared. Our original Y1 was e to the 2x plus U2, so 1/2 x squared plus x. And then our Y2 was x e to the 2x. And I mean, we can clean this up a little bit. let's see. We'll keep the e to the 2x together. We're going to have a minus 1/3 x cubed plus a 1/2 x cubed. If you distribute this x, you get x cubed and then x squared here. So minus 1/3 plus 1/2 is 1/6 x cubed. And we have minus 1/2 plus 1 x squared, so that's plus 1/2 x squared. So this is the nicer version of our particular solution, and now we can say what our general solution is. Our general solution will be y equal to what? What is yc, yep, which is the complementary function, which is good, plus particular solution, which we have above. And there it is. You will get the same answer if you chose to annihilate. I'll give you guys one to try. It does not necessarily only work for second order. You can expand the concept here. Instead of a 2x2 determinant, you're going to have a 3x3 determinant. Does that make sense? So it's going to get a little, yeah. But it's the same idea, same principles. And this is a great example for the variation of parameters method because can we annihilate cosecant 3x? We cannot, so we don't really have a choice. What should you do first, just to make sure we don't? Yes, you always want that lead coefficient to be 1. Okay, you guys work. Oh, you know what? I don't want this to be prime. Scratch this guy out. Just 36y. So here's the equation you guys are working on. Try not to look up at the answer. I'm going to just put it up here so that if we're watching the video later, they have a way to check this.